I want to find the derivative, find y prime for the following. I'm trying to make it not super duper ugly. Let's make it something like similar to the quiz. Let's make it x to the 6 times y cubed plus equal to, sure, equal to tangent of x, y squared, sure, plus, this is y, this is going to be gross. And there is, I will say this specific thing, when you have like tangent of something with x and y in it, multiplied together, or really every kind of a product or one-sided chain rule, usually there's an additional extra algebra step. So I'm going to solve this. I'm going to differentiate both sides just like we always do. Differentiating both sides. And please stop me if you have questions. Differentiate both sides. Use the product rule here. So we get 6x to the 5th times y cubed plus, then we do it the other way, right? We leave the x to the 6th alone. We multiply by the derivative of y cubed. Sorry, I said x to the 6th or x to the 3rd. The derivative of y cubed, or some stuff cubed, is 3 times my stuff squared times the derivative of my stuff. So it's going to be 3 times y squared times y prime. That's the left-hand side. And stop bouncing. There we go. Okay. And the right-hand side is going to be, so the derivative tangent of some stuff is secant squared of that stuff times the derivative of that stuff. And for the derivative of x by squared, we have to use the product rule. So it's going to be derivative of x, which is 1, times y squared, plus x times the derivative of y squared, which is 2y times y prime. Lastly, the derivative of 5y to the 4th, sorry, the derivative of y to the 5th is 5y to the 4th times y prime. Are there questions about this first step, where we've just taken the derivative of everything? Okay, before we can isolate the y primes or bring them all to one side, this specific problem requires, I feel like, an additional step where here we have to distribute. We have to distribute this secant squared of xy squared to each of these terms that is being multiplied by. And the reason we really have to is because one of them has a y prime in it and one of them doesn't. And we can't really separate the y prime from the not y prime until we deal with this. I feel like I've seen other people maybe do different things with this. I've never done it other than this. So here's, and I'm also going to simplify it a little bit on the way. So now 6x to the 5th y cubed plus 3x to the 6th y squared y prime equal to secant squared of xy squared times y squared. I'm going to write the y squared first, because it's pretty standard to put other variables before trig functions. And then I'm going to have 2xy y prime times secant squared. It's also standard to write constants before other things. So 2xy y prime times secant squared of xy squared plus 5y to the 4th y prime. And then we're going to identify all the things that have a y prime. So those 3 things have a y prime, the other 2 things do not. So bring all 3 things that have a y prime to one side and all the other things to the other side. And I don't really care which side. I would probably bring this over there and not over there, just because it feels like you're moving less stuff, but it doesn't really matter. If you pick, so the one thing I will say is if you pick the other side, like if I bring my y primes to the left, right, and you bring yours to the left, our answers will look slightly different, and the top and the bottom will be the negatives of each of my like your top and bottom will be the negatives of my top and bottom, but you're essentially just taking my answer and multiplying by -1 over -1, which is still the same. So it's okay to bring it to either side. You're still going to get the answer, or at least picking a side won't make it so your answer is wrong. Let's bring all the y primes to the right. So on the left, I'm going to get 6x to the 5th y cubed minus y squared secant squared of xy squared equal to this plus this minus that. And I really shouldn't. So I might do something lazy in a second here, but here's what I know it's for. So I have 2x, y prime, secant squared of x, y squared, plus 5y to the fourth, y prime, minus 3x to the sixth, y squared, y prime. All right, who would like to tell me what our next step is? What do we do next? I probably need to chat up if I actually want to see things that you guys meant, right? Then I have the chat. Exactly, factor out the y prime. And I'm going to be a little lazy about it because I'd really like to not write more. So I'm going to just factor out the y prime. So there's a y prime. There's a y prime. Right, we brought all the terms that have y prime to one side so that we could factor out the y prime. Or divide out the y prime if you prefer that language. And then we're going to divide by what's left. So our final answer is going to be y prime equal to that divided by this garbage. So it's going to be 6x to the fifth y cubed minus y squared secant squared of xy squared divided by 2xy secant squared of xy squared plus 5y to the fourth minus 3x to the sixth y squared. And that is gross. Algebra is not fun, but there's nothing specifically that is extra difficult about this. It is just keeping track. Now, that's not to like, oh, what's the word? There's a word I'm looking for. I don't want to like downplay it, right? It's not that this problem isn't hard. It's a hard problem, but it's hard because the algebra is just messy and we have to be careful about keeping track of it. As long as we are careful, this problem should be very doable. Yeah, that's all I have to say about this one. And you want to do that next. So, yeah. I also want to talk about, so I'm doing problems that are similar to the quiz problems, but not exactly the same, because I feel like if you want to, you can go look at the solutions to the quiz. And so this is just, I'm trying to give you as many examples as possible. Let's talk about a problem where we do find the slope of the tangent line. So slope of line, we can even do the equation if you guys would prefer. The equation of the line tangent to, what do I want to pick here? I want to pick something fun. But not really that fun, so let's just make it easy. So let's do something like x to the fourth plus y cubed equal to, sure. Brain, work brain. X minus y squared to the sixth plus, I don't know, plus, oh, I guess I need the initial plus 2. So I want to say, when you're finding the equation of the line tangent to something, or the slope of the line tangent to something, right, it's really about the slope. Oh, we need a point, sorry. At the point 1, 1. Once you've taken the derivative, so here's the thing, right? If it was a regular equation, like let's say, for example, I said find the equation of line tangent to, y equals, I don't know, 5x squared over x plus 1. Now I want to find the equation of the line tangent to this point at the point when x is 1 and y is, well, y would be 5 over 1 plus 1, so 5 halves. If I was going to find the slope of the tangent line here, what would I do? I would take the derivative. And then what do we do right after we take the derivative? We plug in 1, right? Like, I mean, let's do it. My y prime is going to be the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. And sure, you could simplify that, but why? I'm just trying to find the slope of the tangent line. I don't need to know what the derivative is everywhere. I can know what the derivative is right there. So y prime at 1 is going to be 1 plus 1 times 10 minus 5 times 1 over 1 plus 1 squared, which is going to be 20, I don't really care, it's 15 over 4. But the point I'm trying to make is that once you have taken the derivative of both sides, your only goal is to find what y prime is when you plug in the point. And you can plug in the point whenever you want. And I'm going to plug it in right away because that is the easiest thing to do. So I'm going to take the derivative. I'm going to get 4x cubed plus the derivative of y cubed is 3y squared times y prime equal to the derivative of stuff to the sixth is 6 times my stuff to the fifth times the derivative of the stuff, which is 1 minus the derivative of y squared is 2y prime plus 0, right? Because the derivative of 2 is 0. And now we plug in, right? We don't wait. We don't solve. I mean, you could definitely solve for y prime if you want to. But one, it's going to be a pain here because you have to do this distributed thing. And two, if you don't plug in 1, 1 right away, you miss out on the time-saving fact that when you plug in 1 and 1, this whole thing is going to be 0. So really, a lot of the time, these problems are designed so that if you do the thing where you substitute in your point right away, things work out super nice. So I plug in 1, 1 right now. I get x is 1 and y is 1, and y prime is what we're solving for. So I get 4 times 1 plus 3 times 1 times y prime equals 6 times 1 minus 1. Oh, that's 0 times I don't care. 0 times anything is 0, right? So this is all 0 over here. So it doesn't matter what, 6 times 0 times 1 minus 2y prime. Still all 0 because we multiply by 0. So what do we get? Well, we get y prime super easy, right? We get 4 plus 3y prime equals 0. 3y prime equals negative 4. Y prime is negative 4/3. So here's what I haven't done. I haven't found the derivative everywhere. I've only found the derivative at this one point. But that's all I was being asked to do. So the derivative of 1, 1 is negative 4/3. So then the equation of my tangent line would be y minus the y coordinate equals negative 4/3 times x minus the x coordinate. And you could solve for y if you want to, but all right, well, not really just one, but one more explicitly implicit differentiation question. And someone asked me this one, and I kind of had a question about it. And I don't remember who asked it, so if you know about this question, please feel free to chime in, because I don't. But the question was to find the second derivative of y cubed equal to sine of x, I think. Let me double check and see if that's right. Where'd you go? Yeah, no, sorry, sine of y equal to x cubed. And the process was to find the second derivative. And I wasn't sure if the point was to use implicit differentiation or not. We can do this using implicit, but I'm really not sure if that's what was intended. Does anybody know or have an idea of what so one way is to use implicit. The other way we could do it, it would be to solve for y. And we could solve for y by writing y as the inverse sine of x cubed. And I'm not really sure. So they want us to use arc sine? Okay. You could also do it using implicit. It'd be kind of funky, but it would totally work. So doing it, so we have two different answers. All right, well, let's do it both ways. So let's do it using, let's do it this way first, because this way is a little bit more straightforward, I think. But we have to actually know the derivative of the arc sine of x, which we did talk about at the end of last class. I'm going to write on the other side of the board. We will definitely talk more about arc sine today, but for now, I'll just say what it is, because we did do it last class. And so if your function is the arc sine of x, or if you prefer the inverse sine, I prefer arc sine, but some people like inverse sine better. It's okay. Your derivative, dy dx, is 1 over the square root of 1 minus x squared. So I'm going to say the chain rule thing I always say. If I know the derivative of arc sine of x is 1 over the square root of 1 minus x squared, I know the derivative of the arc sine of some stuff is 1 over the square root of 1 minus the stuff squared times the derivative of the stuff, right? It's always the same deal. You're just replacing x with stuff and multiplying by the derivative of stuff. I'll be right back. Sorry, one second. Sorry, it's getting warm in my office. My wife turned on the heat because she is too cold and my office is too warm. But anyway, that's life. So, derivative of the inverse sine of some stuff is 1 over the square root of 1 minus the stuff squared times the derivative of stuff. And then before taking the second derivative, I would simplify this. So I would probably write this as, so 3x squared on top over 1 minus x to the 6th to the 1/2. And now your choice is either to do quotient rule like this or bring this up as 3x squared times 1 minus 6 x to the 6th to the negative 1/2. I don't really care which way to do it, but we can do it either way. I'll come back to the implicit here. So the second derivative would be, so bottom, right here is just quotient rule. Bottom, derivative of the top, which is 6x minus the top. I need more room. Yeah, there's never enough room. Sorry. Yeah, I guess I'll just try and write small. Second derivative is bottom times the derivative of the top, which is 6x, minus the top, times the derivative of the bottom, which is going to be a little bit messy. It's going to be 1/2 times 1 minus x to the 6th to the negative 1/2 times the derivative of x, negative x to the 6th, which is negative 6x to the 5th, over the denominator square, which is just going to be 1 minus x to the 6th. Yes, there's simplifying to do here. No, I don't really care to do it. But if you
What happened to the 1/2 in the denominator?
Say that one more time.
What happened to the 1/2 in the denominator? Because aren't you supposed to square the denominator?
Right, exactly. And if you have something to the 1/2 squared, it's just the stuff something.
Oh, okay.
Right?
Yeah.
But if I take like the square root of 5 squared, it's just going to be 5. That's what's happening there. Okay. I will just mention, if you really wanted to simplify this more, you could factor out a 1 minus x to the 6th to the negative 1/2 on top. Maybe we'll do that. If you guys want to do that, we can do that. But let's talk about the other way before we talk about factoring. Because I feel like the other question was the one that might have been the one that was more being asked. So the other way of looking at this was, let me remind myself here. Why can't I see my stuff? Because I'm blind. There we go. Sine of y equals x cubed. So let's try and take this derivative, the second derivative implicitly, which is always kind of funky. Second derivative implicitly. Take the first derivative. So the first derivative, so just differentiate, I should say. We're not really taking it here. There's sine of some stuff is cosine of the stuff times the derivative of stuff equal to the other side. Solve for y prime. And then, this is going to be interesting. So then we're going to take the second derivative. Again, using the quotient rule. So it's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom, which is negative sine of y. I'm gonna make it a negative with a positive sine of y times y prime. Hopefully everyone's okay with that. Over cosine squared. Yeah. So there isn't a question yet, but so before we think about anything else, one thing we have to do is we have to replace y prime with what it's equal to. Because when you're finding the second derivative, it should at least be in terms of x and y. So y prime is this mess here. So I'm going to rewrite this as cosine of y times 6x plus 3x squared times sine of y times 3x squared over cosine of y over cosine squared y. And I'm not sure if that's where we need to leave it or not. There are things we could do, but they kind of start getting weird. I will point out, though, you could totally replace sine of y with x cubed. And you could totally replace cosine squared is 1 minus sine squared of y, which is 1 minus x cubed squared, which is 1 minus x to the 6th. Oh, that sounds familiar. The denominator is 1 minus x to the 6th. So our answers are the same. They just look very different. But again, I'm not really sure if the question is asking us what exactly the question is asking us to do. If I was told to do this problem using implicit, I would probably leave it here without starting to replace things. But you can replace all the things. And I feel like that's kind of maybe part of the point of the problem. So I will actually say one more thing, and that's that cosine of y is the square root of this. So we can also replace that with that, and that with that. And then essentially we've got the same answer, right? We've got 1 minus x to the 6th to the 1/2, which is cosine of y, times 6x, minus, oh, did I make a mistake? No, oh, that's interesting. Interesting. So then we've got, our answers do look a little bit different because of, sorry, I keep like swinging the board back and forth because it is an interesting problem, right? So this whole thing here, we'd have to figure, sorry, I'm thinking like, oh, this is super cool. We would get a 3x to the 5th. Okay, I'm not going to run this problem too much anymore. Needless to say, it's interesting. And you can definitely, there are lots of things to see here. But it kind of actually goes back to the derivatives of the inverse trig functions in general. So hopefully that was at least something of a sensible answer to what that question was. The thing I want you to take away from that, if nothing else, is that when you take the second derivative implicitly and you get your y prime showing up, you have to then replace that y prime with what y prime is actually equal to. That's kind of the big piece of second derivative implicit differentiation. But then you will see a lot of books and people start replacing things like, oh, I know the sine of y is x cubed. So you'll see a lot of that happening as well in these second derivative implicit problems. Okay. I feel like we should back up a step though before we get too deep into the inverse trig functions. I feel like we should talk about the derivative of the inverse function just in general, because there is a formula for it and it's kind of weird. It's one that honestly, every time I think about it, I have to kind of remember how it works. So let's remember how it works. I want to find the derivative of the inverse function. And so the way I'm going to think about this is I'm going to say, okay, well, I've got some function y equals f of x. And I'm going to say it's invertible, right? It has an inverse. And the inverse means that if y equals f of x, then f inverse of y is equal to x. Right? That's what inverse functions do. Regular function has input x, spits out y. Inverse function has input y, spits back out x. Some classic examples are exponential and logarithmic functions, right? Like y equals 2 to the x versus log base 2 of y equals x. Here, we input 3, we get out 8. Here, we input 8, we get out 3. Now, the thing is, people don't usually write it like this, right? They usually then switch the x and y back so that they can write it more like a regular function of x. And they say, oh, we write it as f inverse of x equal to log base 2 of x, because the notation just works better if we call things in terms of x. All right, that's kind of the idea. Now the idea is that I want to take the derivative of f inverse. So here, I want to find the derivative of f inverse. So here's what I'm going to do. I'm going to use the chain rule. I'm going to say that f of f inverse of x is equal to x. This is true, right? For functions that are invertible, f inverse does something, and then f undoes it. So, right, f inverse of y gives us x, and if we plug back in x, we get back y. But we're using x instead, right? Because the notation, again, is just easier. So I could also say, right, f inverse of x is equal to something else, like, I'm not going to use y because I don't want to use y. It's equal to j. That's the same as saying f of j equals x. So f inverse of x equals j, and then f of j gets us back to x. Okay. And now we're going to use the chain rule to take the derivative. I'm going to take the derivative of f of some stuff. Well, it's going to be f prime of the stuff times the derivative of the stuff. So the derivative on this side is going to be f prime of my stuff. Sorry, I got an extra stray mark there that I did not want. Times the derivative of this stuff. On the right-hand side, the derivative of x is 1. And now we're going to isolate this so that the derivative of f inverse of x is equal to 1 over f prime of f inverse of x. And that's the formula. But usually they do it at like a point A or something instead of at x. But that's the idea, is if you're differentiating the inverse of a function, you're doing 1 over the derivative of the regular function evaluated at where the inverse is. Which I know is kind of, it's not the easiest thing to necessarily wrap your head around right away. I'm going to look at one notational thing just to be sure that I'm not doing something stupid. No, I'm not doing something stupid. Great. I will say, usually people do, so I do want to point out that, like, so here, no, that's, yeah, it gets, no, I don't want to say that. All right. So let's look at an example. In fact, let's look at a really well-known example. Let's say our function is e to the x. What's the derivative of e to the x? Well, it's e to the x, of course. But I want to find the derivative of the inverse function. So I want to find the derivative of the inverse function. And I know the inverse function of e to the x is the natural log of x. I know what the derivative of natural log of x is, so do you. It's 1 over x. But we're going to do it this weird, funky way. We're going to say, instead of saying it's just 1 over x, we're going to say it's 1 over f prime of f inverse of x. F prime is e to the x. So f prime of f inverse is e to the f inverse. But f inverse is the natural log function. So this is 1 over e to the natural log of x, which is 1 over x. How do I say this the right way? Sorry, there's words I'm about to say. I want to make sure that they're very precise. This formula for finding the derivative of the inverse is really just kind of a shortcut to the process of using implicit differentiation to find a derivative. Like, we could totally, and just did, find the derivative of natural log of x this way. But the way we actually find the derivative of natural log of x back in the day, which, like last week, was we said, oh, I want to find the derivative of natural log of x. Well, we rewrote it as e to the y equals e to the natural log of x. And then wrote that as e to the y equals x. and then just did the implicit differentiation here. Right? The derivative of e to the y is e to the y times y prime equals 1, and then solve for y prime. These two processes achieve the same results. They just feel very different. To me, this feels so much more natural, and this feels so weird and bizarre. But there are good questions we can ask that make us have to use this, so we're not going to ignore this completely like I have before, because I wanted to. I will also point out, you can totally use that formula for the derivative of any of the inverse trig functions. It's just super funky. Let's do that, and then we'll actually do a real example. Let's say I want to find the derivative of the inverse sine function. And instead of doing it the normal way, well, the way I think is normal, I'm biased, okay. The way we did it last time, we're going to instead say, all right, I'm going to say the derivative of inverse sine is going to be 1 over, the problem is notation here, right? My regular function is sine of x. My inverse function is inverse sine of x. And so to take the derivative of inverse sine of x, it's going to be 1 over f prime of f inverse. Which is 1 over, so f prime derivative of sine is cosine. So it's 1 over cosine of my f inverse, which is inverse sine of x. Now, I know this doesn't look like the answer that we got when we did it last time, because it's the not nice way of writing it. But I will say, right, this is my f prime of f inverse. And then this is where I use a triangle, you might do something else, right? But f inverse of cosine of sine inverse. In fact, I don't want to get too tangenty here, pun intended. But we should talk about how to evaluate inverse sine. So let me ask you guys a quick question. What is the inverse sine of 1/2? Or even better, what does that even mean? Well, when I read inverse sine of 1/2, I'm reading the function that does sine but backwards, or undoes what sine does. I know sine of an angle in radians, pi over 6 to be precise. I know that sine of pi over 6 is equal to 1/2. And the inverse trig function reverses the order of the input and the output. So the inverse sine of 1/2 is equal to pi over 6, right? Inverse functions, input and output, interchange. A lot of I words there. Inverse, input, yeah, okay. Interchange. So when I see inverse sine of 1/2 or inverse sine of anything, the words that happen in my head are, I'm looking for the angle whose sine is equal to that number, 1/2. Or in this case, I'm looking for the angle whose sine is equal to x. So that's what I'm going to draw in my triangle. I'm going to draw an angle, theta, and inverse sine of x is equal to theta, which theta, not 0, which also means that sine of theta is equal to x. Sine is the opposite over the hypotenuse. And if I find this third side using the the Pythagorean theorem, it's going to be the square root of 1 minus x squared. And then if I find the cosine of this angle, inverse sine of x, cosine of inverse sine of x is square root of 1 minus x squared over 1. So this is exactly equal to 1 over the square root of 1 minus x squared. So if it really floated your boat, does not float my boat, if it really floated your boat, you could totally use this inverse function derivative. I don't even know what it's called. Is there a name for it? The derivative rules for inverses. That's what Theorem 3 is in the book. You could totally use this to find derivatives of inverses of functions we already know derivatives of. It would be most useful for like natural log and the inverse trig functions, and that's kind of about it. However, some clever people, not me, came up with some good questions. like, oh, that's good too. Yeah. Like the following. So here is a typical question that kind of forces us to use this theorem. Find the slope of the tangent line, of the line tangent to the inverse of the function f of x equal to x cubed plus, sorry, x to the fifth plus x cubed plus x at the point. So usually the people I've seen do it are kind of, the way I've seen books do it are kind of real, there's not a good word for what I want to say that isn't kind of crude. They're kind of not nice about it in the book sometimes. They'll say find the slope of the tangent line to the inverse of this function at, I want to say at, what do I got here? Yeah, at x equal to 3. So the idea is we have to use the theorem. Now, first of all, can we use the theorem? Is this function even invertible? Well, yes. And the way you know a function is invertible, well, one way to know a function is invertible is if it's always increasing or always decreasing, right? A function has to pass the horizontal line test to be invertible. And any function that's always getting bigger or always getting smaller from left to right is definitely going to pass the horizontal line test. Okay, so the problem with trying to answer this in a more straightforward way is I can't find f inverse, right? If I do the thing like how we normally find f inverse where we switch x and y and then try and solve for y, that's going to be a problem. So if I switch x and y, this is y, so it becomes x. Y to the fifth plus y cubed plus y. I'm not solving for y, right? That's not going to happen. You're not either, right? No one is solving for y. It's not doable here. So we're kind of stuck. Whereas like the other examples we could actually kind of solve, here we can't. So we have to instead use this inverse derivative theorem, which says, okay, well, I know that the derivative of f inverse at a point is equal to 1 over f prime of f inverse of 3.
Is that the formula for every inverse derivative theorem?
Yes. Yeah, and in fact, so I'm looking at page, well, my book's a little old. I'm looking at Theorem 3 in section 3.8, the derivative rule for inverses, where if you're trying to find the derivative.
What page is that? What page is that? Because I also have the 12th edition.
Okay, it's page 177.
All right, thank you.
I do have the 12th edition, right? Yeah, I do. Okay. So, f prime is not a big deal, right? We know how to take the derivative here. F prime of x is equal to 5x to the fourth plus 3x squared plus 1. The harder part here is what's f inverse of 3? So if I'm trying to find f inverse of 3 equal to x, I should really call it y. That doesn't matter. That's the same as saying, oh, f of y should equal 3. So here's what I'm doing, right? I'm trying to find a number where if I put it into the inverse function, I get out some value. Well, that means that value I'm trying to get out here is what I would have to put into this function to get back out 3. So let me ask you guys. And so the idea here is that they usually try to make it kind of obvious. What could I plug in for x and maybe get 3 out as my answer? Right. They're usually going to make it something that is like, you're probably going to be plugging in 0 or 1 or something very straightforward. So yeah, So f of 1 equals 3 means f inverse of 3 is equal to 1. So this part here is 1. So then we're going to get 1 over f prime, which is this function, evaluated at 1. So that's going to be 1 over 5 plus 3 plus 1, which is 1/9. And no, I can't do that, sorry. Yeah. The reason this kind of works, or the reason this does work actually, is really because of there's some symmetry that inverse functions have, right? If you look at, so let me actually just share this other example with you guys. Yeah, no, I don't. Sure, let me share this example. Come on, sure. So I'm looking at this example right here. How does the slope of this function, x cubed plus 1 at x equal 2, compare to the slope of f inverse of x at x equals 9? And I will point out, in this function, f of 2 is 9, and f inverse of 9 is 2. So if we look over here at 2, the derivative, which is 3x squared of the original function, is going to give you f prime of 2 is going to be 12. And that kind of makes sense. Right? If you look at the 0.29 here, the slope is very steep. The slope is 12. For the inverse function, so we can actually find the inverse derivative. The inverse function is the cube root of x minus 1. Right? We can solve this for x. And then the derivative of that is 1/3 x minus 1 to the negative 2/3, which is 1 over 3 x minus 1 to the 2/3. And if you plug in the 0.9, 9 minus 1 is 8. 8 to the 2/3 is 4. 3 times 4 is 12, and you get 1 over 12. So I want to point out that, right, the derivative of the inverse is 1 over the derivative of the original function, evaluated at the right point. Right? So the derivative of f inverse at 9 is 1 over the derivative of the original function at, in this case, 2. And that makes sense because of the symmetry, right? These graphs, it's drawn pretty well. These graphs are symmetric across the line y equals x. So if you go from the 0.29 to the 0.92, the slopes of the tangent lines should invert, right? This one's super steep. This one is the reciprocal of that super steepness and is super shallow. So hopefully that makes a little bit of sense about why this formula actually works the way it does work. And so here we can write it this way. The derivative of f inverse at b is 1 over f prime of f inverse at b. Kind of funky. Let me stop sharing here. So that's the idea with this theorem, is that you can use it to answer kind of weird questions. Let's do one more, just because I've certainly seen students get kind of caught up with this before. We'll do one more, then we'll take a break. Then I think we'll hit the trig inverse functions hard. I feel like there was something else that was also on my mind, but I'll have to figure that out. So let's say I want to find, what do I got here? Let's say my function is e to the negative x squared plus x. Which probably invertible. I'm not usually going to worry about the invertibleness, really. So I want to find the derivative of the inverse function at x equal to 1. Now I want to really kind of emphasize here, we're not plugging 1 into this, even though we've kind of used notation that would lead you to think that. We're going to use the formula, because that's all we've got, right? I could not interchange x and y here and solve for y. It just is not doable. So I'm going to find the derivative of f inverse of x as 1 over f prime of f inverse of x. Or really, I mean, sometimes people like write a little like a vertical line evaluated at a point. I just kind of like to throw it in and do it again. So my function is f of x equal to e to the negative x squared plus x. My derivative is e to the negative x squared times the derivative of negative x squared, which is negative 2x plus 1. All right. And now I need to figure out what I'm trying to plug in, right? I'm trying to evaluate this derivative at 0. So I need to know what f inverse of, sorry, I gave it away. Trying to evaluate this at 1, which means I need to know what f inverse of 1 is equal to. Well, what could I plug in for x that might make this equal to 1? There's only really, especially when you've got e to the something, there's only like one number you want to try. And that's usually going to be 0. Because e to the 0 is an integer, and e to the anything else that's typical to plug in is not. So I'm like, oh, it's probably 0. Because, oh yeah, f of 0 is definitely e to the 0 plus 0, which is 1. So then we're going to say, okay, so I want to find f prime of f inverse of 1 equals 0. So I want 1 over f prime of 1. Sorry, not f prime of 1, f prime of 0. I just said that and then I wrote the wrong thing. And that's going to be 1 over, so f prime of 0 is going to be e to the 0 times 0 plus 1, which is 1. So that's how this theorem works. You have to find the inverse function evaluated at your point. So basically, if you're not given the inverse function, you say, okay, instead of figuring out what f inverse of 1 is equal to, I have to figure out what do I plug in into my function to get it equal to 1. That's what we did here. We said, oh, 0 is the thing you plug in to get 1 out. And then you evaluate the derivative at that point. Right? The derivative at that point, and then you do the reciprocal of that. Let's talk about some more derivatives, inverse trig functions. And then I also remember I need to talk about related rates today. So we'll try and, those are two kind of big topics, but we can do some of both. So let's talk about the derivative inverse tangent for a second, which I also know, I think we talked about last class very briefly. So I do want to make the connection between the two different ways of doing this. One being the thing we just talked about, the inverse derivative theorem formula, whatever you want to call it. And the other being what I think was the more normal way using implicit differentiation. So one way you could do it is just say the derivative inverse tangent. So again, I'm thinking of my function f of x as tangent, and my inverse function is inverse tangent. Then you could use the formula that says, oh, the derivative of a function, the derivative of the inverse function is 1 over the derivative of the function, and the derivative of tangent is secant squared, evaluated at the inverse function, right? This is 1 over f prime of f. This is f prime of f of x. F prime of f inverse, sorry. Okay, right? Our function is tangent, the f prime is secant squared, the inverse is inverse tangent. So you get 1 over secant squared of inverse tangent. Or you could do it what I think was the more normal way, where you say, oh, I've got y equal to inverse tangent. I'm going to rewrite this as tangent of y equal to x, either by just saying, well, if y equals inverse tangent is the angle that if you take tangent of it, you get x. Well, I'm calling it y, and I'm taking tangent of it, and I'm getting x. And then we're going to take the derivative of both sides. You can, yeah. So secant squared of y times y prime, right? The derivative of tangent, secant squared of some stuff times the derivative of stuff, equals the derivative of x, which is 1. And solving for y prime, look, we get the same thing. We get 1 over secant squared of y, but y is inverse tangent. So either way you slice it, you're going to get 1 over secant squared of inverse tangent of x. The thing is, what do you do then? Because that is definitely not what we know the derivative of inverse tangent to look like. Well, there's a couple ways to go about it. My preferred method is to do a triangle, to use a triangle. We say, okay, well, tangent of y equals x, or if you prefer, x over 1. Tangent is opposite over adjacent. opposite over adjacent, and then we find the third side using the Pythagorean theorem. The third side is the square root of 1 plus x squared. And then we can find secant. Let's see, cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent. So secant of y is hypotenuse over adjacent, which is square root of 1 plus x squared. And then secant squared of y is just 1 plus x squared. So we get 1 over 1 plus x squared. This is not the only way to do it, but it is the way that I think is the best. Some people like to do this using trig identities, which also works out just fine. If you really, really want, you can say, oh, I know a trig. I will have to. This is my favorite trig identity. It is 1 plus tangent squared of whatever equals secant squared of whatever. I'm using y's because my things have y's in it. The reason this is my favorite trig identity because one time a student told me, oh, I know how to remember that. It's I tan and get sexy. So I've never been able to forget it. Sometimes I wish I could. But you will never forget I tan and get sexy. 1 plus tangent squared of y equals secant squared of y. But we could use that because then I can say, well, look, secant squared of y is 1 plus tangent squared. But tangent of y is equal to x. So secant squared of y is equal to 1 plus tangent of y, which is x, squared. So you can get there either way. You can get there using trig identities or using triangles. They're really the same because these are the Pythagorean trig identities. But that's how you can get to the derivative of inverse tangent. And so I should say the rest of these inverse trig function derivatives all work out the same. I mean, not the same, but like the process is the same. Especially for cosine and cotangent compared to tangent and sine. So here's what we have so far. We have the derivative of inverse sine of x is 1 over the square root of 1 minus x squared. Let's do inverse cosine. And I know we have inverse tangents as well, but let's do inverse cosine. So for inverse cosine, I'm going to do it the way I like to do it because I just think it makes sense. So I'm going to write y equals inverse cosine of x. I'm immediately going to rewrite as cosine of y equal to x. I will remind everybody that inverse cosine of x, this has values that are between 0 and pi. So now we're going to differentiate both sides. The derivative of cosine of some stuff is negative sine of the stuff times the derivative of the stuff. And every time we do one of these inverse trig ones, the x is always going to be by itself, and the derivative of x is just 1. So let's solve for y prime. Y prime is 1 over negative sine of y. And you could plug in inverse cosine of x, right? You could totally write this as y prime equals negative 1 over sine of inverse cosine of x. But nobody writes it that way. Instead, what we do is say, oh yeah, cosine of y equals y. Cosine of y equals x. Draw myself a right triangle where y is the angle. Cosine is adjacent over hypotenuse, so that's going to be adjacent is x. Hypotenuse is 1. And the third side, using the Pythagorean theorem, x squared plus blank squared equals 1 squared. So blank squared equals 1 minus x squared. So we get that this is equal to the square root of 1 minus x squared. And then sine of this angle is the opposite over the hypotenuse, which is going to be negative 1 over the square root of 1 minus x squared. Which is nice because it's virtually the same as the derivative of the inverse sine. We already know tangent. Derivative of the inverse tangent is equal to 1 over 1 plus x squared. Let's do cotangent.
When you're writing the triangle, how do you know which side to put the x in the 1?
So I want to find the derivative of cotangent of y. Sorry, cotangent. Oh my gosh. The derivative inverse cotangent of x. Sorry, brain. Come on, brain. So we're going to let y equal to the inverse cotangent of x. And then we're going to say cotangent of y equals x. In some ways, this is, no, it's kind of like logarithmic differentiation, where like you take the natural log of y, simplify the other side, and then you take the derivative of both sides, and the derivative of natural log of y was 1 over y prime. It's not exactly the same, but it's a very similar process. The derivative cotangent of y is negative cosecant squared of y times y prime, again, equal to 1. Solving for y prime, we get y prime equal to 1 over negative cosecant squared is going to be negative 1 over cosecant squared of y. It's funny, every time I've done this problem, I've never taken the time to rewrite this. Say, well, you could write 1 over cosecant squared as sine squared, or you could totally write this as negative sine squared of y. I just never do. We've got cotangent of y equal to x. Cotangent is not opposite over adjacent, but adjacent over opposite. So it's going to be x over 1, where this is my angle y. And I want to make a remark. And the remark is that if you know the same two sides of a triangle, meaning like if you know either both the legs, or you know the hypotenuse and the leg, or hypotenuse, basically, if you know that the hypotenuse is the same as it was before, I'm trying to say something, but it's not turning out very well. Basically, if you know two sides, or those two sides, the third side's still kind of the same as it was here, right? The Pythagorean theorem doesn't really care which leg is which. So whether it's 1 squared plus x squared equals that squared, or x squared plus 1 squared equals that squared, that thing there is still the same. So that this ends up being negative 1 over cosecant is the reciprocal of sine. Sine is opposite of hypotenuse. Cosecant is hypotenuse over opposite. So cosecant is the square root of 1 plus x squared over 1. So it's the square root of 1 plus x squared, which is negative 1 over 1 plus x squared. And so what we're seeing, and this is not a coincidence, this is very much a thing, is that the derivative of inverse sine is that. The derivative inverse cosine is just the negative of that. The derivative of inverse tangent, and I see that I wrote tangent there, sorry about that. The derivative of the inverse tangent is 1 over 1 plus x squared, and the derivative of the inverse cotangent is negative 1 over 1 plus x squared. And the same thing is going to be true for arc secant and arc cosecant, or inverse secant and inverse cosecant. So let's do inverse secant. Okay. The secant ones are maybe the moment where we should actually take a minute to talk about the graphs of these functions. So, yeah. The problem is, in fact, let me show you. So, I imagine your teacher said something about this. Sure. One second. Yeah, let me just show you using Desmos because I think that'll be useful. So when we graph, y equals sine of x, and I think I said this last time, but I'm not positive, so I'm going to say it again. Let me share here. When we graph y equals sine of x, it's a perfectly fine function. But if we try and graph the inverse relationship, not a function, right? X equals sine of y really fails the vertical line test. So what we have to do is we actually have to restrict the domain of the sine function to be from negative pi over 2 to pi over 2. Oops, I hate when that happened. When you start writing a fraction, you forget that you're in there. Yeah. And we're going to restrict the sine function to that. So then we can restrict this function to the same sort of thing. Except we're going to make that a y. So there's your inverse function. There's not a whole lot to it. I'm going to close it, right? So there's your inverse sine function. And we can actually just write y equals inverse. At least I think we can. Let's find out. I don't know if this is going to appreciate that notation or not. No, they're like, we don't like you. Maybe just do arc sine. That would be smarter. Yeah. No, that's interesting. I wonder why it like doubled up like that. Maybe because there's lots of fun points to find. Anyway, the same thing is true for all the trig functions. If you do tangent, it's super funky, right? Like you get lots of stuff. And if you did the reciprocal, or sorry, the inverse, not reciprocal relationship, x equal to tangent of y, it's going to look bonkers. Kind of neat, right? Like I think that's pretty cool, but it's just your tangent function turned on its side. Or really, I should say flipped across line y equals x. And it's kind of fun when you draw them both, like, ooh, you're making some fun graphs. That's kind of neat. Anyway, we do the same sort of thing. Just like we restricted sine of x to that domain, we do the same thing for tangent. And then we just get one of the intervals from negative pi over 2 to pi over 2. And we can do the same thing over here. And we get that. So there's your inverse tangent graph, all nice and happy. Now, there's a problem with secant. And I'm actually curious to know how Desmos defines it. So in fact, let's actually draw secant first. So there's secant. And the problem with secant is there's not everyone agrees where we should cut it off, right? Because we want to make it one-to-one. We all agree for cosine. For cosine, everyone's like, oh, cosine, we want it to be one-to-one. We're going to cut it off and make it from not negative pi over 2 to pi over 2, but from 0 to pi. Because look, that's one-to-one. And if we invert it, we get exactly y equal to the arc cosine of x. So there's the green one, that's the arc cosine. But now here's the thing about inverse secant. Well, here's the thing about secant, I should say. We could do secant from here up to there, and then from way down here to here. And there's a perfectly good, legitimate reason for doing it that way. The reason I like that choice is because that's where cosine is also chosen to be. And secant and cosine are pretty much, they're reciprocals of each other, so it kind of is like, oh, that seems reasonable. But there is another good reason to go from 0 to pi over 2, which is like, well, can I 0 to pi over 2, and then from pi to 3 pi over 2, which is kind of weird, but there is a good reason. Specifically, the derivative is nicer if we pick that. So let's see what Desmos says, just because I'm super curious. If I do the arc secant, they're like, we don't graph that for you. Okay. So they're making the choice. So notice, right, that the choice here, you have y going from 0 up to pi. So they're making the choice of that there. So I have to ask everybody. And again, this isn't a huge deal. Sorry, I'm gonna stop sharing. That's not my video. For those of you that have learned about the derivative of the inverse secant, is there an absolute value in your derivative or not? So did you guys learn that the derivative of the inverse secant of x is equal to 1 over x times the square root of x squared minus 1? Or is it 1 over the absolute value of x times the square root of x squared minus 1? Or have you guys not done it yet? Well, either way, here's what I'll say. Your book definitely does it with the absolute value. Okay. So here's the deal. We choose inverse secant. I should back up. Everybody agrees. All the other four trig functions, sine, cosine, tangent, cotangent, all have nice, easily agreed upon inverse trig functions. Secant is the exception. This book does the following. They say, okay, I don't need an asymptote there. From 0 to pi, we're going to draw this portion of secant where there's an asymptote right in the middle. And we're going to do this. And we're going to do, that's 1, -1. We're going to do this. That's the part we're going to cut off or restrict the domain to. And then the inverse, so this is y equals secant of x, where x is restricted to be between 0 and pi. And the inverse is going to look like, well, when you invert things, you just interchange x and y. So 0, 1 becomes the point 1, 0. The vertical asymptote pi over 2 becomes the horizontal asymptote pi over 2. And the point pi negative 1 becomes the point negative 1 pi. And it looks like this. But I will mention that there are some texts, some people, that instead of using this part here, use this part here. And instead of having this part here, have that part there. And I'll say why in just a minute. So let's find the derivative of inverse secant, doing the same thing we've done for all the other ones. So I'm going to let y equal the inverse secant of x, which means secant of y equals x. And then we're going to differentiate both sides. The derivative secant of some stuff is secant of the stuff times tangent of the stuff times derivative of the stuff. So the derivative here is going to be secant of y times tangent of y equal to 1. Oh, I forgot the thing. I forgot the y prime. So then I'm going to solve for y prime. Y prime is equal to 1 over secant of y times tangent of y. Secant of y is easy. It's just x. Tangent I have to work harder for. I need a triangle. So tangent, let's see. So secant is hypotenuse over adjacent. So it's x over 1. This third side is the square root of x squared minus 1. And tangent is opposite over adjacent, which is the square root of x squared minus 1. And you would be thinking, well, this seems like it should be the answer. What's this absolute value garbage you're talking about? Well, here's the problem. If you look at the graph of the derivative, if you look at the, you could look at the graph here. If you look at the graph of the inverse function, what do you notice about whether it's increasing or decreasing? Is this graph in blue, what's it doing? Is it always increasing? Is it always decreasing? Is it sometimes doing some of the other? Hearing nobody say anything. It is, I like my sound's on, right? Yes, my sound's on. It's always increasing. Any tangent line I draw is going to have a positive slope. Right there, positive slope. Or right over here, positive slope. The problem is that this isn't always positive. If my derivative is always positive, my derivative should be always positive. The square root of x squared minus 1 is always positive, at least if we're in this domain where x is bigger than 1 or less than negative 1. X over here is not always positive. So we have to throw on an absolute value there to make it so it agrees with our graph. On the other hand, if your teacher decides to depart from the book and say, we're going to do this instead, the reason you do that is because then you get to say, we don't have to have an absolute value. So here's the short of it. The derivative inverse secant is 1 over the absolute value, maybe, of the square root of x times the square root of x squared minus 1. Sorry, I should say 1 over the opposite value of x times the square root of x squared minus 1. And the really nice thing is that the derivative of the inverse cosecant is the negative of that. It's negative 1 over the opposite value of x times the square root of x squared minus 1. So you should definitely memorize these. Inverse secant and inverse cosecant come up less, but all the rest of them come up quite a bit. And really, you only have to memorize inverse sine, inverse tangent, and inverse secant. And then you know that the inverse cofunctions are all just the negatives. Right? If you know inverse sine, you definitely know the derivative of inverse cosine. If you know inverse tangent, you definitely know the derivative of inverse cotangent. If you know inverse cosecant, you definitely know, secant, you definitely know the derivative of inverse cosecant. And the really nice thing is that just like with the regular trig derivatives, all of the co-functions, cosine, I wrote these out of order, and now I feel terrible about it. Usually I write cosecant up there and secant down here. Sorry. But just like with the regular trig functions, all the co-functions, cosine, cosecant, and cotangent, all those have negative derivatives. So it's a nice kind of pattern that is continuing to happen. And then, of course, we can go on and do like some chain rule versions of these. And then we will do some related rates, because we need to talk about related rates. Okay, so chain rule version, we can take the derivative of the inverse tangent of x cubed plus 5. And this is just throwing everything at the formula again. So just like the derivative of inverse tangent of x is 1 over 1 plus x squared, the derivative of inverse tangent of some stuff is going to be 1 over 1 plus your stuff squared times the derivative of your stuff. It's the same thing again and again and again. So it's 1 over 1 plus x cubed plus 5 squared times the derivative of x cubed plus 5. Or here's a question that someone actually asked me about, which I think is a good example. I feel like this one came up because it simplifies in a funky way or a nice way. The derivative of the, where'd you go? Natural log of x squared plus 4 minus x times arctangent of x over 2. Okay, so let's do the derivative of the natural log of x squared plus 4. It's going to be 1 over the stuff times the derivative of the stuff. And then the derivative of this, we're going to have to use the product rule. So when I have a minus a product rule, I usually think of it as minus, and then it's all of the product rule that I'm going to take the derivative of. So it's going to be the derivative of x, which is 1, times arctangent of x over 2, plus x times the derivative of arctangent of x over 2, which is going to be 1 over 1 plus x over 2 squared times the derivative of x over 2, which is just 1 over 2. Now, you could leave it like this, but I feel like there is more to this problem than just this. So let's simplify it a little bit, because I'm pretty sure this part here and this part here might actually cancel out, which I think is kind of the point of this problem. So I'm going to write this as 2x over x squared plus 4 minus arctangent of x over 2 minus, so what have I got here? I've got x over 1 plus x squared over 4, and then I've also got a 1/2. Yeah, so here's what I'm going to do. I really want to get rid of that 4. So I'm going to multiply, well, I already got it, I'm just going to do it the easy way. I would multiply this by 4 over 4. And look what happens. I get 2x over x squared plus 4 minus arctangent of x over 2. And then I get minus 4x over, distribute the 4 plus x squared times 1/2. Cancel a 2 here and a 2 here. And this, and this, are the same, so they cancel out because this one's positive and that one's negative. So you end up with just arc tangent of x over 2. It's kind of a good question. So later on, when you take Calc 2 and you have to find the antiderivative of arc tangent of x over 2, you're going to get something like this. Kind of interesting. That's when you get the integration by parts in Calc 2. But that is still a whole quarter away because we're just getting the integration by parts in Calc 2 in 21B right this week. So yeah, anyway. Sometimes it's good to simplify things. I mean, that's usually good to simplify things. Sometimes you see stuff cancel if you simplify things. So hopefully whoever asked you that question in their reflection, hopefully you got to see that. I'd love to talk more about inverse trig derivatives because I think they're really fun, but I should probably at least throw a couple related rates problems our way. So let me grab an example here. Let me see what I want. Sure. Right, okay, we can do that, sure. Let's talk about, so I guess we should do a basic example because, So suppose the radius of a circle, and imagine you've seen an example like this already, it's okay, is increasing at 2 feet per second. How fast is the area changing? When the radius is 10 feet. So I know this is a fairly straightforward example of this, but what I really want to impart to all of you is the process for attacking any related rates problem. And that process is always a 4-step, sometimes a 5-step process. The 5th step, which is really the first step, is sometimes it makes sense to draw a picture. Here, I don't really think you can draw a picture. Or you can draw a picture of a circle. Maybe you can. And the radius, you're like, okay, the radius is like getting bigger. So the circle is getting bigger. Sometimes the picture is a lot more helpful than others. But my first step is always to identify what's changing. Now, I know that's not always super specific. Really, the question is to identify the thing they've told you is changing, because for sure they've told you how at least one thing is changing, and to identify the thing that you're trying to figure out how it's changing. In this case, those things are the radius and the area. They've told us how the radius is changing. They're asking us how the area is changing. So radius is changing, and I know how the radius is changing. It's increasing at 2 feet per second. So I'm going to write that dr dt, the rate of change of the radius with respect to time, is equal to 2. And I guess I could write, r here for radius. And you can write the units. I don't always write the units, but sometimes I do. And my area, I don't know how the area is changing, but I want to. So I'm going to write down, well, I want to know what dA dt is, the rate of change of the area with respect to time. And it's equal to, I don't know, although I can talk about the units. The units for how area is changing should be square feet per second, or square unit of measurement per unit of time. Okay, so that's step 1, identify what's changing. Step 2, you want an equation that relates the non-time variables. Almost always this is going to be some sort of geometric equation, meaning the area of the circle, or the volume of the sphere, or the area of the triangle, or it's going to be something that has to do with geometry, or like the Pythagorean theorem, or similar triangles, or something where you have to be like, okay, there's a formula to connect these two things. In this case, it's just the area formula for a circle. The area is equal to pi r squared. All right, I want to make it really, really clear before we do this next step. I want to find how the area is changing with respect to time. I want to find that. I'm trying to find d. I don't even see that yet in my formula. Right? There is nothing that says that is there yet. And I'm also pretty sure I'm going to use this. What I'm trying to imply here is that both of those things need to actually show up when we do this next step. And the next step is to differentiate both sides of the equation with respect to time. It doesn't always have to be with respect to time, but it's almost always with respect to time, because usually you're talking about how things are changing as time is progressing. So I'm going to differentiate implicitly, really. So I've got A equals pi r squared, and both area and, in fact, I could write it like this if I really wanted to. I could write A of t equals pi times r of t squared. I didn't differentiate yet. I'm about to. What's the derivative here? It's A prime of t. And the derivative here, so the derivative of pi times some stuff squared is 2 times my stuff to the first times the derivative of that stuff. Now here's the thing. Mathematicians are lazy. They don't write this all out this way because it's just so much. Instead, we use this notation. We say, oh, instead of A prime of t, I'm going to write dA dt. And instead of, well, I'm going to write 2 pi instead of pi times 2. But instead of r of t, I'm just going to write r. It's implied that r is a function of time. And then r prime of t, I'm going to write dr dt. So, right, if I had just started with this and used implicit differentiation, where t is the variable that I'm differentiating with respect to, the derivative of a is the derivative of a with respect to t, and the derivative of pi r squared is 2 pi r times the derivative of r. Just like if it was y squared, the derivative would be 2y times y prime. Here, the derivative is 2r times r prime. So, when you're differentiating both sides, you want to think, oh yeah, everything's a function of time. If it's more complicated than just a, where the derivative is the derivative of a, you have to use the chain rule / implicit, same thing really, to get the dr dt shown up. And then finally, plug in and solve. So we should normally be able to plug in for everything that we don't know and solve for the one thing that we're trying to find, which is this, which happens to be, luckily this time, all by itself. So I'm going to get dA dt equal to 2 pi times the radius, which is 10 feet, because they asked us how fast is the area increasing when the radius is 10 feet, times the rate of change of the radius, dr dt, which is 2 feet per second. And notice, now normally I wouldn't write the units. Normally I would just write 2 pi times 10 times 2, and so that my answer was 40 pi. And then at the end I'd be like, oh, what should the units be? Well, the unit should be area per time, so feet squared per time. But if you also look here, I get feet times feet per second, so I get feet squared per second. So that's an example of how to do a problem like this. And I really, really, really strongly recommend every time going through this process. First figuring out what's changing, then finding an equation that relates them, then taking the derivative of both sides with respect to time, then plugging in and finding what we want to do. So let's look at, I think I can squeeze in 2 more examples. So what I've got here. So the radius of a cylinder is increasing at 3 inches per minute. And the height is decreasing at 4 inches per minute. How fast is the volume changing? when the radius is 8 inches and the height is 5 inches. All right, same process. I guess a picture maybe is in order here. So here's my cylinder. It's got a radius of r, height of h. I should say, when you are drawing a picture and labeling things, which we'll show in the next example, things that are changing, you want to give variable names because they're changing. But things that aren't changing, if there are any of those, you want to give those the names of whatever they're actually equal to. Right, so, you might be like, oh, wasn't the radius 5? No, the radius is changing, but we're asking how it's changing or how the volume is changing when we happen to be at the precise moment when the radius is expanded to 5, right? We're taking that snapshot and asking, what's the rate of change right now? So what's changing? Well, the radius is changing. We know that dr dt is equal to 3 inches per minute. What else is changing? Well, the height's changing. We know that dh dt is negative 4 inches per minute. Right? If something is getting smaller, its derivative is negative. Its rate of change is negative. So be aware of that. And finally, volume is what we're trying to actually figure out how it's changing. So we want to know what dV dt is. And although I don't know what it is yet, I know that it should be having units that are inches cubed per minute. All right. We need an equation relating the volume, height, and radius. There's definitely an equation for the volume of a cylinder. It's the base area, which is a circle, times the height. So the volume of my cylinder is pi r squared h. And now we're going to differentiate both sides. And in this case, this is kind of atypical, but in this case, we're going to have to use the product rule. So I'm going to get dV dt equal to, I'm just going to think about the constant pi as just hanging out front. And I'm going to do the derivative of r squared h. So I'm going to do the derivative of the first thing. What's the derivative of r squared? It's 2r dr dt times h. And there's my derivative of r squared times h plus, now leave r squared alone and multiply by the derivative of h. So this is the derivative of r squared. This is the derivative of h. So you get derivative of r squared times h plus r squared times the derivative of h. And then we plug in what we know and we solve for what we don't. So we're trying to figure out dV dt, so I'm going to plug in all the stuff for r and dr dt and h and whatever. So I'm going to get the dV dt is equal to, so r is 5 inches, so I'm going to get 2 times 5 inches times dr dt is 3 inches per minute. Times h, which is 8, plus r squared, which is again 5 squared, times dh dt, which is negative 4. And simplifying that, let's see, what do I get? I'm going to go up here. 2 times 5 is 10, 10 times 3 is 30, 30 times 8 is 240, and then 25 times negative 4 is negative 100. I feel like I made a mistake. Oh, well, I know. So the mistake is not that big a deal. The mistake is that I switched the radius and the height values, but that doesn't really matter. Oh, I forgot the pi. I think, yes, I did forget the pi. So I get 240 minus 100 times pi, which is 140 pi cubic inches per minute. So this is increasing at a rate of 140 pi cubic inches per minute. I will say that the other way this goes, so I actually meant for the radius to be 8 and the height to be 5. If those are your numbers, you actually get a negative dV dt at the end, which means the volume is actually decreasing. But that didn't happen here. Yeah, we got time for one more. Let me see. Let me think of which kind of one do I want to do? Do I want to do? Yeah, we should do one of those because that's a good place to go. So. Okay, so here is our last example. I'm going to try and go a little bit quicker. So water is being poured into a conical tank with a radius of 3 feet and a height of 12 feet. So here's our conical tank. Let's say it's conical with a radius of 3 feet and a height of 12 feet. And we're pouring water in, so water goes in at a rate of 3 cubic feet per minute. I'm pouring the volume of water in at that rate. How fast is the water level rising when the water is 6 feet deep? And we would imagine that as the water gets higher, the rate of change of the water height or water level is going to be slower, right? Because in the beginning, it doesn't take very much water to fill up the bottom part, so it's going to get higher really fast. But then as you go later on, it takes a lot more water to fill it up to the next height. So here's what we know. Oh, I suppose I should label some stuff, right? So we've got the water, and its height is it's rising, so that the height is changing, right? We're pouring water in. And so it's also got a radius that is also changing. And we want to know, well, here's what we know. So we know how the volume is changing. We know that dV dt is 3 cubic feet per minute. And we want to know how the water level is changing. So we want to know what dH dt is. Right, that's what is of interest. That's what they're asking us about. Now, I know that the radius is also changing, but we don't know how it's changing, and we're not asked about how it's changing. So although it might be important, I'm not going to write it down yet because we don't know it. So the second thing is to write an equation involving all the non-time variables. Now, here's the equation for the volume of a cylinder, of a cone. It's 1/3 the volume of a cylinder, actually. It's 1/3 pi r squared h. And here's the problem. If I differentiate this one like I did the last one, I'm going to get r and r prime, or dr dt, and I don't know dr dt. So here's what we do with these cone problems. And there's kind of an easy way and there's a hard way. The big cone, the radius is 3 feet and the height is 12 feet. And that ratio is always true no matter how big your cone, or no matter which cone you're using in this cone. Meaning you can always say that the radius is 3/12 the height, or the radius is 1/4 the height. You could also, if you wanted to get more kind of specific about it, you could use similar triangles. You could say, oh, look, here's a triangle with radius and height. And oh, look, here's a similar triangle with a height of 12 and a base of 3. So you can say, oh yeah, r over 3 equals h over 12, and get the same sort of thing. But the way I really actually think about it is I always think is, oh, the big cone is the ratio for all the other cones. And in this big cone, the radius happens to be 1/4 the height, because 3 is 1/4 of 12. What that means for us is we can replace the radius with h over 4, or 1/4 h. So I can rewrite this equation as 1/3 pi times h over 4 squared times h, which I would then simplify before I differentiated. I would write this as H over 4 squared is h squared over 16. And 1 over 16 times 1 over 3 is 1 over 48. So I write this as pi over 48 times h cubed. And this is really kind of the key thing that always has to be done for these cone problems, is you have to take whichever one you don't want and solve for the other one. So here, right, you can always write radius and height as a ratio because they're always in the same ratio because it's a cone. So then we can differentiate both sides and say that dv dt is equal to pi over 48 times 3h squared times dh dt. Right, the derivative of h cubed is 3 times h squared times the derivative of h. And then finally, we can plug in what we know. We know that h is 6 feet, right? We're asking what's happening with the height of 6 feet. And we know that the rate of change of the volume is 3 cubic feet per minute. So I'm going to erase because I need this room. So plugging in what we know, dv dt is 3. It's equal to pi over 48 times, I could have canceled the 3, oh well, times 3 times 6 squared times dh dt. Then we can definitely cancel some stuff. 3 and 48 you can cancel. 16. So 3 equals pi over 16 times 36 times dh dt. Probably cancel a 4 here and a 4 here. So 3 equals 9 pi over 4 times dh dt. Multiply both sides of the reciprocal, and you get 4 times 3 over 9 pi equals dh dt. Canceling a 3 there and a 3 there. You get 4 over 3 pi feet per minute is equal to dh dt. How fast the height of the water is changing. So again, I will say, all of these related rates problems at some level are the same. Meaning, you always know how something is changing. You're always asked how something related is changing, or its related rate. And then you find an equation relating those two variables. Sometimes you have to do some extra garbage where you have to get rid of an extra variable because it's problematic. But then once you have just the variables you want, you can differentiate both sides, and then you can plug in what you know and solve for what you want. And they always kind of follow this pattern of that process. So I really encourage you, if you have a related rates problem, don't just don't go at it sporadically. You really want to kind of do it systematically, where you're like, well, I'm going to do this first, and then this, and then this, and then, right? Like it works.